Hello everyone and welcome to this video. In our previous video, we have studied the theorem based on rational numbers and irrational numbers. Now we will discuss decimal expansion of rational numbers. Can you write the decimal expansion of these rational numbers? To practice this, pause the video to try and then check your answer. Can you tell which method have we used here? Perfect! We have used the division method here. What do you understand by looking at these decimal expansions? You studied in your last class that the decimal expansion of a rational number p upon q, where q is not 0, will either be terminating, like here. The decimal expansion of 33 upon 8 is terminating. Or non-terminating, that is repeating, like here, the decimal expansion of 2 upon 11 is repeated and non-terminating. Now, the question is, should we use the same method to find out whether the decimal expansion of a rational number is terminating or non-terminating? Or do we have some other method as well? Let's discuss these decimal numbers to find out. You can see that all these can be expressed as rational numbers in this manner, whose denominator is a power of 10. Now, if we write the numerator and denominator in the form of their prime factors, then we cancel out their common factors. Now, what do you see here? We can see here that all real numbers whose decimal expansion is terminating are written as a rational number in the form of p upon q, where p and q are co-prime. And the denominator, that is q, has only powers of 2 or powers of 5 or powers of both 2 and 5. This is because the prime factors of 10 are only 2 and 5. So, the powers of 10 will remain in the form of powers of 2 and 5. Based on this, we can say that if x is a rational number whose decimal expansion is terminating, then x can be expressed as p upon q, where p and q are co-prime, and the prime factorization of q is 2 raised to the power n into 5 raised to the power m, where n and m are non-negative integers. Now, if we look at these rational numbers, then can you guess whether their decimal expansion will be terminating or non-terminating? If we solve by division method, we understand that the decimal expansion of the first and second rational numbers is terminating, and the decimal expansion of the third and fourth rational numbers is non-terminating. If we take the numerator and denominator of these rational numbers in the form of prime factors, you will see that the denominator of terminating rational numbers can be written as 2 raised to n into 5 raised to m, while the denominator of non-terminating rational numbers cannot be written in this format. Thus, we can say that the inverse of the theorem we just studied is also true, which we can formally write as follows. Suppose x equals p upon q is a rational number such that q is in the form of 2 raised to n into 5 raised to m, where n and m are non-negative integers. Then, the decimal expansion of x will be terminating. And if q is not in the form of 2 raised to n into 5 raised to m, then the decimal expansion of x will be a non-terminating rational number. In this video, we discuss the decimal expansion of rational numbers. In the next video, we will see examples based on it. Hello everyone and welcome to this video. In the last video, we discussed the decimal expansion of rational numbers. Now, we will see an example based on it. Here, without using division, we have to tell which rational numbers have a terminating decimal expansion and which ones have non-terminating decimal expansion. Can you guess how to find this out? Pause the video and try to solve this question. If we factorize both the numerator and denominator of this first rational number, we find that the denominator is in the form of 2 raised to n into 5 raised to m. In our previous video, we learned that in a rational number p upon q, if q is in the form of 2 raised to n into 5 raised to m, where n and m are non-negative integers, then the decimal expansion of the number is terminating. So, the decimal expansion of this number is also terminating. Let us now discuss the second rational number, 17 upon 15. After analyzing it, we see that the denominator is not in the form of 2 raised to n into 5 raised to m. You will remember that in a rational number p upon q, if q is not in the form of 2 raised to n into 5 raised to m, then the decimal expansion of the number is non-terminating. Similarly, we can also find out the decimal expansion of the remaining rational numbers. So, the decimal expansions of the first, fourth and fifth rational numbers will be terminating. And the decimal expansions of the second and third rational numbers will be infinitely recurring, that is, non-terminating. In this video, we saw examples based on decimal expansion of rational numbers. In the next video, we will see interesting examples based on real numbers. Hello everyone and welcome to this video. In the previous video, we saw some examples based on decimal expansions of rational numbers. In this video, we will see some interesting examples based on real numbers. So come on, let's discuss these real numbers. What can you tell about these numbers by looking at them? These are all real numbers, and real numbers are a set of rational and irrational numbers. So first, we look at these irrational numbers. Can you guess what their decimal expansions would be like? We know that the decimal expansion of all irrational numbers is non-terminating, non-repeating. Now, let's move to rational numbers. Moving forward, if we observe the decimal expansion of this number, we can see that these 3 points at the end of the number tell us that the decimal expansion is non-terminating and the digits after the decimal 8, 3, 4, 5 and 6 are recurring. So, the decimal expansion of this real number will be non-terminating. Repeating, we can also write this number in this way by putting a bar. What do you understand by this bar above the digits? This bar above the digits represents the group of digits that are recurring. Like in this number, the digits 2 and 7 are recurring. So, the decimal expansion of this rational number will be non-terminating. Repeating, so we can say that if a number has a digit or a group of digits with this bar above them, the decimal expansion of that number is non-terminating. Repeating, now, if we look at 29 upon 1000, we can write it straight as 0.029 based on the knowledge of our previous classes. Or, we can factorize the numerator and denominator as the denominator is in the form of 2 raised to n into 5 raised to m. Both ways lead to the same conclusion that the decimal expansion of this rational number will be terminating. Because we learned that in a rational number, p upon q, if q is in the form of 2 raised to n into 5 raised to m, the decimal expansion of such a rational number will be terminating. And if q is not in the form of 2 raised to n into 5 raised to m, the decimal expansion of such a rational number will be non-terminating. Repeating, as you can see in this number. Now, find out the decimal expansion of this rational number using the rules that you have learned in this video. In this video, we discussed real numbers, rational numbers, and irrational numbers.